The latest wave of agent frameworks promises to make software autonomous, optimizing skills, memory, and security for coding environments like Claude Code and Cursor. But a dangerous illusion has taken hold among engineers that better code equals smarter machines in the real world. We are conflating digital optimization with physical capability. When you try to deploy these agents on actual hardware, they hit an unbreakable wall of sensor latency and actuator limits that no software patch can fix. Today, we separate the hype from the mechanical reality of what it actually takes for a machine to move in the physical world. To understand why this gap exists, we must look at the fundamental nature of these systems. Current research indicates that modern AI agents are formally equivalent to Chomsky hierarchy automata. This is a mathematical classification describing finite state or pushdown machines. It means their intelligence is strictly bound by software memory constraints rather than physical agency. They operate as perfect logic engines within a digital sandbox, but they lack the embodied reality required for robotics. An agent can write flawless code in an editor, yet it has no access to the tacit procedural knowledge of what happens when a motor stalls or a sensor drifts due to temperature changes. This distinction is critical because we are witnessing a massive misallocation of engineering effort. Teams are pouring resources into optimizing context windows and memory retrieval for agents like ECC, believing that scaling these skills will unlock true autonomy. However, the hardware bottlenecks remain untouched by software tricks. The primary failure mode of autonomous agents is not cognitive but sensory actuator latency. No matter how many tokens you expand, or how complex your skill library becomes, you cannot write a function to overcome the time it takes for light to travel from a camera to a processor and back again. You also cannot code away thermal limits on an actuator that overheats under load. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This leads us into what can be described as the McNamara fallacy within embodied contexts. Current agentic systems optimize rigorously for measurable digital proxies, such as task completion rates in simulation or token efficiency scores. They fail catastrophically when they encounter unstructured physical variables like friction coefficients, material wear, and gravity that define real-world hardware bottlenecks. A simulation can perfectly model a robot picking up an object if the physics engine is tuned right, but it cannot account for the micro-variations in surface texture or the slight play in a gear train that causes a grasp to slip. The agent sees a perfect digital match, but the physical world delivers chaos. The consequence of this disconnect is profound when we consider deployment risks. Safety analyses warn that escalating autonomy without grounding in hardware reality increases severe risks like data exfiltration during transmission or loss of life due to unanticipated mechanical failure. We are seeing systems attempt full hardware control prematurely because they assume software optimization translates directly to physical performance. In reality, these agents struggle with persistent memory and long context constraints even within digital environments alone. They cannot close the feedback loops required for true autonomous discovery without extensive simulation that inevitably fails to capture the noise of nature. Consider the specific limitations imposed by this architectural gap. LLMs trained on text data have never felt a broken screw or heard the hum of an overheating motor. This absence means they lack the intuitive understanding of failure modes that human operators develop over years of physical work. When an agent encounters an error in the real world, it often tries to reason its way out using logical rules, rather than sensing the immediate physical state and reacting with reflexive control loops designed for safety. The result is a system that looks intelligent on paper but behaves unpredictably when faced with the chaotic constraints of electromechanical hardware. We are currently measuring these systems against benchmarks that test single-turn digital accuracy. These metrics tell us nothing about how an agent performs under the latency and sensory noise of real-world robotics. A perfect score in code generation does not guarantee a robot can navigate a cluttered warehouse or manipulate fragile objects without crushing them. The synthesis reveals a significant knowledge gap. While we have software artifacts optimized for logic, we lack systems engineered as robust physical actors. Bridging the simulation to reality divide requires fundamental design shifts beyond simple scaling of model parameters. The path forward is not to make agents smarter in isolation, but to ground them in mechanical reality. This means prioritizing sensing fidelity and control latency over context window size. It means designing architectures where software optimization serves hardware constraints rather than trying to override them. We need systems that understand their own physical limits, knowing when to stop because a motor cannot push any harder or a sensor is too noisy to trust. Until we treat these agents as mechanical entities first and digital processes second, the gap between what they can do in code and what they can achieve on Earth will remain unbridgeable. The future of autonomous systems lies not in writing better scripts for existing hardware, but in rethinking how intelligence interacts with matter. We must stop expecting software to solve problems that are fundamentally physical until we build machines where the digital and mechanical layers are inseparable partners rather than separate domains. The engineering reality is clear. You cannot code your way out of physics, no matter how many skills or instincts you try to simulate in a virtual environment. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.